Good afternoon, everyone. Hello.
Yes, hello, doctor.
All right. If you hear your name, please unmute yourself to say you're here. Faisal Khalid. براء حمزة.
موجود يا دكتور، موجود.
وليد محمود. وسيم عبد الباسط. محمد أيمن.
موجود
محمد عادل.
حاضر موجود.
يوسف علي.
حاضر.
حمد سلطان.
حاضر يا دكتور.
خالد هاني.
حاضر.
عبد العزيز خالد.
حاضر.
صالح علي.
حاضر.
فراس سعيد. حسام محمد.
حاضر.
يزيد عبد الله. حسام محمد هير.
يس يا دكتور.
ويزيد عبد الله. نو. فضل عباس. بدر ربيع.
موجود.
فضل عباس. مهند سعيد.
موجود.
محمد حسين. مازن حمدان. عبد العزيز سعيد. هتان أنور.
دكتور.
يس.
عبد العزيز سعيد شفته قبل شوي، أنا كنت في البلاك بورد فأتوقع إنه هو حاضر، بس يعني حرسل له دحين اللينك.
اوكي. هتان أنور.
موجود يا دكتور.
محمد فيصل.
موجود.
بهاء أيمن.
موجود يا دكتور.
يوسف نصار. راكان طارق.
حاضر.
محمد عبد الكريم.
موجود يا دكتور.
معتز أحمد. محمد سالم.
حاضر.
توفيق محمد. أنس عبد الرحمن. عبد الله أحمد.
موجود.
اوكي.
دكتور.
يس.
وسيم موجود، معلش بس كنت في البلاك بورد.
اوكي.
برضه دكتور فراس.
What are you doing in Blackboard؟ ما أعرف أنا أرسلت لينك Blackboard.
من غلط.
It's alright. Anyone else طيب؟ Alright, let's start. How are you guys doing? All good?
فاين الحمد لله.
Ready for the weekend? Alright, let's start. So you have your, you can see my screen, right? Topic 9.
Yes, clear.
Just confirm that you see the change from here to here. Sometimes this does not work. You can see it?
Yes, doctor.
Okay. So today we talk about acceptance sampling plans to be specific. This is your second to last topic for this course. Every time we did the control chart before, it was assumed that we know the sample size per subgroup. Here we know the significance of the sampling plans. Here we discuss a whole new concept of the sampling plans, right? That new concept is not how big n should be. We discussed before how to find n. What is a statistically significant sample? What is a big enough sample statistically? That is not what we are discussing today. We are discussing that if we have a specific population and we take a specific sample from said population, that sample, when there are a specific number of defectives within that sample, do we accept the lot, the entire population, or do we not accept it? Right? Based on that. So it's a sampling plan designed to know if there should be a binary decision of acceptance versus non-acceptance of the entire population. An example of that, an actual sampling plan, are the 3 lines you see in the middle here, right? The big N is 9,000, the small n is 300, then the C equals 2. What does that mean? If you have a lot or a population of size 9,000, and you take a sample, small n, of size 300, and you say that your acceptance criteria, which is C here, is 2, it means that if you find in this sample of 300, if you find 2 items that are defective, or less than 2, or fewer than 2, it means you can accept the entirety of the 9,000. If you have 3 or more, so more than 2, your acceptance criteria, you reject or do not accept the entire lot of 9,000. So that's the procedure of how to look at and interpret a sampling plan. This right here, these 3 lines, is an example of a single sampling plan. Single sampling plan. We will also discuss sequential sampling and double sampling and multiple sampling. So this is, at its most basic form, is a sampling plan. Its category is single sampling plan. Okay? So that's sampling plan for what? For acceptance sampling, which is the form of inspection applied to lots. Whenever we say lots in this course, the meaning is population. It is not the sample that you're taking from it. Okay? The purpose is that to judge conformance to predetermined standards or specification. So you're only judging the conformance. Is this a quality improvement tool? It is not a quality improvement tool. It's a lot sentencing, meaning like in the court of law, you sentence someone to death, you're sentencing this lot of 9,000 to death. You're saying we're rejecting the lot, we're not shipping it to customer. This is called lot sentencing or population sentencing. Are we clear on how to read a single sampling plan now?
Yes.
All right. Moving on. Acceptance sampling. When do we do it? When is it useful? When large numbers of items must be processed in a short amount of time. When, for example, you do not have sensors that can do a 100% inspection, you have to take a sample. When the cost of passing defectives is low, meaning if there is a defective item that goes out to customer and the cost of having a defective item with the customer is so low that you don't care about it, you don't care about the quality, then you use acceptance sampling. Then the meaning here is that acceptance sampling is not very ideal as compared to 100% sensor-based or camera-based inspection, right? When you have to use human inspection, when you have to take only a sample, when the sensor is so expensive, when the detection is so expensive, so that's a backup plan, is that we do acceptance sampling, right? Fatigue and boredom is caused by inspecting large number of items. If that is your priority, is the human factors engineering of it all, and you don't want to bore your workers with this, then you would do acceptance sampling. So acceptance sampling is a backup plan. When the facility is not as sophisticated as some other factories, what we do is we use acceptance sampling when we don't have sensor measurements. Also, it is very important to use acceptance sampling when destructive testing is required. For example, for cars, there is a crash test for safety for the dummies inside the cars, then you would have to destroy the car to know about the safety, right? Here, 100% inspection is very illogical. You're not going to destroy all the cars that you have because you're not going to do 100% inspection. You're going to lose your entire lot. So you're going to have to do some acceptance sampling here, right? Also, if the cost of 100% inspection is so high, whether destructive testing or otherwise, we do use acceptance sampling. When automatic inspection is not available, like the last point here, for example, and feel free to read the rest. When automatic inspection is not available, no sensor measurements, all of those things, we do use acceptance sampling. By the way, if you have any questions, don't use the raise hand feature. Just open your mic and speak because I cannot see that while viewing the PowerPoint. Okay? All right, 3 important aspects of sampling in general. It involves random sampling of the entire lot. Then you either accept or reject the lot. So do the lot sentencing here. You do the lot sentencing, which is what? Either accept or reject. So what we're dealing with here is a binary decision, 0 or 1, accept or reject this lot. So when we do the lot sentencing or judge a lot by a criteria like the 9,302 that we just looked at as a single sampling example, you either accept with no inspection at all, or you inspect all the items that you have, all the 9,000, or you do acceptance sampling, meaning you take that sample of 300 as the example, then determine a specific criteria. In those 300, if I have 2 or fewer, accept. 3 or more, reject. That acceptance sampling is sampling plan design, right? And you just saw in that example, the 9,302, that was the simplest form of acceptance sampling, and it is called a single sampling plan. This one as a reminder, the one in the middle here, okay? Any questions so far? All right. Can you guys hear me? Are you alive?
Yes, we are with you.
Yes, Dr. Orkney.
Yes.
All right. Advantages. So it places responsibility where it belongs. If you do that sampling in a specific shifts, you would know where it is, who are the workers responsible. It is obviously less expensive than what? Than 100% inspection, right? It improves the inspector's job, obviously. Last one, lots are not accepted, which gives motivation for improvement. As I mentioned before, it is not a quality improvement tool. Acceptance sampling is only an observation tool. Lots are not accepted, so it only gives you motivation to actually do the quality improvement. So when you do acceptance sampling plan design, it is exactly like doing a control chart, seeing that there are points out of control, and then doing nothing. Doing no revision, doing no investigation to know the assignable causes. That control chart of not doing a revision and not doing an investigation is not a quality improvement tool. It's a quality monitoring tool, right? Here, acceptance sampling can be a quality improvement tool if you act on it after the fact. If you see that you're rejecting too many lots, too many populations, if every population is a shift, that can be a motivation to actually improve the quality. Know the assignable causes and do some corrective action. Do some preventative action for future lots, right? All right. Disadvantages is obviously the first and most important one is the risk of accepting bad lots and rejecting good lots. So when you reject good lots because you found in your sample of 300 out of the 9,000, you found 3 items, right? Let's say we're rejecting this lot. Let's go back to the example. You see this right here? Population 9,000, sample 300. We saw that C is 2. We saw that items inspected, we had 3 defectives. So what do we do in this case? We reject the lot, correct?
Yes.
Okay. This is a risk of rejecting this lot of 9,000 based on only this 300, when maybe if we took a different 300, we might have 2 or less and not reject the lot at all, right? Which means this sample should be, first of all, the safest thing is to have it truly randomly selected. We have to remove the bias of selecting this sample. It should not be a sample that we like or the closest to us on the factory floor or the first one in the shift, or it has to be truly random by using a random number table, something just so we can at least remove the bias when we do this, right? This is not an ideal situation. Acceptance sampling is not an ideal situation. We do it to save time, to save money, while compromising and having that risk of rejecting the entire 9,000, right? The entire 9,000. So that's the biggest disadvantage of acceptance sampling, is that risk of accepting bad lots and rejecting good lots. Because accepting bad lots, meaning products will go out to the customers because it came out of an accepted lot, even though it is bad, because the sample you took was also biased and it showed you that there was no defects. It was biased and it was not representative of the entire population of the 9,000 in our example. In addition to these other disadvantages, like no assurance the entire lot conforms or doesn't conform to specs or to specification. So we're dealing with a specific probability here of acceptance. And we will try to also determine that probability of acceptance based on the proportion of defectives within a sample. We'll try to do that as well in acceptance sampling to improve the usability of acceptance sampling. We're going to discuss that later on in the topic, the probability of acceptance, okay? So as you know, on the left you see here sunglasses or 3D glasses that are a lot, a sample of them, you already know what that is. I want to discuss with you the different sampling plans that we will discuss in this topic. Some of them today, we discussed the single sampling, and we'll discuss the ones after that later on. Is it a 0 or a 1? We don't know if the lot should be accepted or rejected. If we don't know, then we have to take a second sample, and that is called the double sampling plan. If we're not sure about the second sample, we move on to multiple sampling plan, where we have thrice as much samples to take, or 4 times as much. We quadruple our effect of sampling, or to a point where we reach sequential sampling at the end, right? Or 100 inspection, that part of it is sequential sampling. We'll get to the details later. Anyway, we start with single sampling. This is just to tell you the terminology of a single sampling plan. It is the same example we discussed at the very beginning. Capital N 9,000, small n 300, and then the acceptance criteria is 2. N is the lot size or population size, and that can be a specific shift in a factory. That sample that we take from that shift is small n, which is the sample size, the acceptance number, and please be careful, the acceptance number, if it is 2, like in this example, we do accept if it equals to 2, or equals to 1, or equals to 0, all those 3. We don't reject if it's a 2, we reject, so it is C equals to or less, or fewer. That is our acceptance criteria in a single sampling plan. That is the definition of the C number. All right, a single sampling plan is one where that sample should be representative of the population. Each item is examined, and then after it's examined, it's classified as either good or defective. So purely binary, right? So we're dealing with a binary classification problem here. 0 or 1 only, that's it. It's not how many defects overall per unit, and no. Every product, is it considered defective or not now? If yes, we count it as the first one. Another one, 2. A third one, we inspected, not defective. So far we have 2, we're good. The fourth one, defective, we now have 3. By this definition of this single sampling plan, we have a rejected lot. And we move on. Is that clear?
Yes, clear, doctor.
Clear, doctor.
So in a double sampling plan, you can imagine that we have not only one acceptance number, we have C1 and C2. We have another acceptance. And let's say we said if it's 5 or more, R1 is 5. If it's 5 or more, we reject. So we know when to accept, we know when to reject. How about the numbers between 2 and 5? The 3 and the 4. This will create uncertainty. This is how we created the uncertainty. If we get to that, we get to 3 or 4, what do? We take a second sample. How big is it? N2 big. And when we take it, we judge it by what? By its own C2 and R2. Let's look at the example so that can make sense a little bit. Our example is the lot is 9,000, N1, the size of the sample is 60, then C1 is 1, R1 is 5. So if we have only one defect in this 60 in N1, what do? We accept the lot. If we have 5 or more, what do?
We reject it.
We reject because it's R1, R stands for reject. Good. If it is 2 or 3 or 4, the numbers in between, now we have uncertainty. We don't know to accept or to reject. What do? We take a second sample. Second sample is N2. It is here 150 in this example. Okay? We notice that N2 is bigger than N1 because we had uncertainty here. When we want to make sure, we increase N2. So by design, when you design this for yourself, N2 should always be bigger than N1, or at least equals to it. It should not be lower than it. Some of you might say, well, I already looked at 60 samples. The second one should be smaller. I already have some defects here, 2 or 3 or 4. Why should I look at a bigger sample? You should look at a bigger sample because you're taking a second sample anyway now. You should take a bigger sample just to make sure that your lot should not be rejected. You already took the effort of taking a second sample. Let's make it a little bit bigger, right? That's the rationale here, okay? So now that we decided to take the second sample, we have an acceptance and rejection criteria. If it is 6 or less, we accept the entire lot of 9,000. If it's 7 or more, we reject the entire lot of 9,000. Is there an in-between between the 6 and the 7? No. Is this intentional? Yes. Why? Because it's a double sampling plan. We stop at taking 2 samples. If we had uncertainty here, so if this was 6 and this was 8, if R2 was 8, the uncertainty will be created at the number what?
7.
7. And if that is the case, what do? We take a third sample, then it becomes a multiple sampling plan, not a double sampling plan. So whenever you end your sampling, you end it where you don't create uncertainty. And these numbers get closer to each other the bigger the sample gets, right? So it's 6 and 7, and there is no integer in between. So to recap, if there is, as it's written here, 1 or fewer items because of C1, we accept the lot. If it's 5 or more, value of R1, we reject the lot. If it's in between 2 or 3 or 4, we take a second sample. How big is it? 150. In that 150 sample, is C2 equaling 6 or 7? If it's 6 or less, we accept. 7 or more, we reject. Is this 6 now or 7 that we found in the second sample? Is it only the second sample? No, it is not. It is a summation of the defects in the second sample plus the first sample. You see the definition of C2 and R2 here? Acceptance number for both samples. Non-acceptance number for both samples. Meaning, we move on to N2 equals 50 and we take that second sample. When do we do that? We do it if we had defects 2 or 3 or 4, right? Between 1 and 5. If it was 2, we see in the second sample of 150, if we had a 4 defects plus the 2, that's a 6 overall, then we accept. If it's 7 overall, we reject. So we count the defects that were in between the 1 and 5 in terms of how many they were. Is that clear?
Yes, but doctor, I have a question.
Yes, please.
Doctor, is there a logic between in choosing like a number of 6 and 7, or it was random?
No, it is not random. The logic is that the 6 and 7 are more than the 1 and the 5, right? How intense they are depending on how strict you want your sampling plan design to be. The important thing is that they are more.
Yeah, that's clear. Thank you.
Yeah. Any other questions before we move on? Okay. Multiple sampling plan is the same as the double sampling plan, but we simply allow room for uncertainty, meaning we don't have a 6 and a 7 like this here. We allow room for uncertainty so we can do a third M that will be M3 and continue the same procedure as we go, right? That is called a multiple sampling plan. But in sequential sampling is something completely different. It is not a single sampling plan. It is not a double sampling plan. It is not a multiple sampling plan. Sequential sampling is that you start from the beginning in all the products that you have. You have 9,000. Take the first item, see if it's good or not. Second item, third item, fourth item, until you hit a constraint. That constraint can be time or cost or whatever it is. When you hit that constraint, you stop. So sequential sampling is costly, and it usually depends on a specific constraint where you stop, right? It does not depend on a specific design of how many do you have or how many defectives. You define an arbitrary number and you stop at it, or you see the overall percentage and you define then after the fact, you define that threshold of where to stop, or that constraint that actually made you stop your sampling. All right. Now we move on to after sequential sampling. So which one to use? Do we use single sampling? Do we use double sampling? Or do we use single sampling plan? Let's consider one of these factors. We have simplicity, cost, units inspected, information, psychological impact. Simplicity. The single sampling is the simplest one, right? The one we discussed in the beginning. It's the simplest one to implement mathematically and yourself and logically. We saw that it is less complicated than the double sampling where you have uncertainty and so on, right?
Yes.
So when I say that, I don't mean just by hand, when you're just looking at it, or by you're eyeballing it and saying it's simple, we should go with it. There is a trade-off involved. It is simple, but there is more risk of rejecting more lots that are good. That's why double sampling is better in terms of accuracy, obviously, because you're taking a second sample and checking. But simplicity here is not just about you as a person working manually. It's also about the computer. There is something called computational efficiency. How fast a computer can do something. It is more difficult for a computer to implement a double sampling by means of a search algorithm to look for the uncertainty and take a second sample and do the calculation for you. That is more complicated on the computer to do than a single sampling plan. So we're considering simplicity in terms of time here as a constraint, not just for you to do it mathematically, manually, but also for the computer itself, right? Is that clear as a concept?
Yes, clear.
Any questions so far? I want to discuss the last one here, psychological impact, right? Psychological impact. Cost is very self-explanatory and so on, but psychological impact is an important one. It is the best under double or also multiple sampling, because the psychological impact of someone actually doing the test and taking the sample. Imagine yourself in the shoes of that inspector and doing only a single sampling plan, where it is you will still have doubt, right? What if I took a second sample and something was more wrong than what I just looked at? What if I rejected the lot from the first sample, and then in the second sample and third and fourth and all the multiple samples that I would take, everything would be okay? So only the first sample was biased, something was wrong with it. I rejected an entire lot and wasted all that money for the 9,000 units because of this. That uncertainty keeps being removed time by time and iteration by iteration when you do double sampling, then multiple sampling, and so on. So as a feeling, you'd have more confidence, right? The statistical significance and the confidence intervals that we do are why? Because you want to have more confidence in your results. You want to reduce the cost. You want to increase customer satisfaction. This is why we do quality management before quality control and industrial quality control, right? That's why we're doing it, for customer satisfaction. That's it. As economically as possible, right? As cost reductingly as possible. That's what we want to do. All right? Any questions so far? All right. Considerations before inspection. So the lots should obviously be homogeneous or homogeneous. Can anyone tell me what that means?
That they are the same.
That they are the same, coming from the same family of products or the same product, things like that. You can't reject a lot based on a sample from a different lot, things like that, right? Larger lots are preferable than smaller lots, but we also have to consider that the sample should be big enough the larger the lot becomes, right? And is that a problem in terms of cost or not? Right? Some considerations in lot formation you have here. Then after that, sample selection. So the units selected for inspection should be chosen at random. Why? Because we said we want to remove the bias. Because if bias is involved in selecting the items in a sample or selecting the sample location itself, then there is no benefit from anything we're doing here. If there is bias, then whether you accept it because of the bias. If you reject it because of the bias. Both situations create a conclusion that is not true about your lot or your population, which is why you have to use location, random number tables. You have to stratify your sample Can anyone remind us? We discussed that in the review for statistics. What is sample stratification?
It's making sure that you're taking a correct sample.
Taking what, sorry?
Correct sample.
The correct sample. What is your definition of a correct sample?
By definition, will be the number of sample maybe, and what is the way that I collect the sample with.
So the statistical significance of a sample comes from how big the sample is as a proportion to the population itself, in addition to where is it collected from. Is it based on the beginning, in terms of time? Is it the beginning of the shift, the end of the shift, or in the middle? Or did you choose it at random? If someone specifically says it's the beginning of the shift, I don't want to wait until the end and see. Let me collect a sample that was produced at the beginning of the shift, then that is not stratified sampling. This is biased on when the machine was perfect in the beginning of the shift. Maybe the machine got broken in the middle of the day, and most of your samples, most of your lot, that is the entire shift, is broken. And you take a sample from the beginning, then everything else, then most of the lot is bad, right? So this is not stratified. Stratified should be at random, so you can minimize your chances of being biased towards something. That something in this example here is the machine producing perfect product in the beginning. You get the idea?
Yes.
So stratification is very important here.
Doctor, I have a question, please.
Yes.
Is the type of my study or my case maybe make me more biased into something?
The type of your study, you're saying?
Yes. If my study is looking for how good is the machine in the beginning of the shift, so I will take a sample from only the beginning of the shift. Okay, if this bias will improve the quality of my study or not?
Yeah, it will improve, but you need to take multiple days now, and every time it should be at the beginning, right? You're going to take 10 days now. Every time your sample is coming from where? From the beginning of the shift, correct?
So
but
being biased or not,
which
it depends on the
days to
student.
choose? Which days to choose now? That should be stratified. Don't focus on only weekends, for example, right? Unless weekends are your primary focus and scope of your study. Then you find something else to randomize your collection.
Okay.
Do you get the idea?
Yes.
Yeah. Okay. Next is non-accepted lots. What do we do with non-accepted lots? They are rectified prior to next process. Meaning, let's say we took a population of 9,000, we took a sample of 300 from it, and then we found 5 items that are defective. Based on this definition, the lot is rejected, right? 9,300, and we found 5 non-conforming to specification. Then we're going to reject the lot, right? When you reject a lot of 9,000 here, what do? You have to rectify all the wrong items in this 9,000. You have to inspect all the 9,000 at 100% inspection. Look at them one by one. See what else is there other than the 5 and the 300 that you found. So you look at the remaining 8,700 items one by one and rework every one that needs rework. Then that lot can go to the customer with 100% accuracy. At the next lecture, on Sunday, we're gonna actually discuss how to do that and what is the percentage of satisfaction of the customers in terms of the items that they receive. Okay? This rectification before the beginning of next process is very important. Very important. Why is it important? And how does it save money and time? Now, when you did that with the first population of 9,000, then a second population, then a third population, and a fourth population, And then in the first 300, you found 5, you rejected. The second one, you found 2, you did not reject. So you don't have to rework when you found the 2. But the one that you had the 5, you have to rework the entirety of the 9,000. So here you saved some time and money by not reworking every population. Right? That's the idea of rectification here. The 100% inspection happens after the non-acceptance sampling or the acceptance sampling. Is that clear?
Yes, doctor.
All right. The last subtopic we discuss is the OC curve, the operating characteristics curve. This curve assesses how good a sampling plan is and tells you a probability of acceptance that you should have based on the sample, right? Let's look at this curve and see how it works. Let's look at this curve. On the y-axis, the curve shows the lot fraction, or shows the probability of acceptance, the probability of acceptance. And on the x-axis, it says in the sample, what is the percent of defect? Let's see that with an example and see how it looks like. If in a sample, the percent of defect is 2.3%, it means that the probability of acceptance of the entire lot is going to be 66%, and that is determined by this curve. How do we draw this curve? Is by finding these points first, these x's, and connecting them to each other. Now, we know how to read this from here to here, right? It's very straightforward. But we don't know how to actually find these points. Let's find out how we can find these points so we can connect them, so we can have a curve, so we can use this feature of reading the probability from the percent of defectives in the sample. Reading the probability of what? Of accepting the population. This OC curve is for a single sampling plan for a population of 3,000, a sample of 89, and an acceptance criteria of 2. How do we find the x's? These x's are numbers from a table. The step 1 to do this is that we have to assume values, and the general recommendation is that we should assume at least 7 different values. That is the minimum requirement for an OC curve or an operating characteristics curve. The minimum requirement, we should assume 7 values, and these are the values here, and they should be from between 0 and 1. Okay, not 0 and 0.1, between 0 and 1, any number, right? These values right here, the 0.01, are assumed. You choose them yourself. If you're asking about questions in the course, sometimes I give you those assumptions and you continue with them. Sometimes I ask you to do it on your own. Choose 7 different values at least. Or I tell you, choose some values to create a curve, and then you choose a 5 and the recommendation is 7, then that's not good enough, not as good as 7. So we are going to follow the general recommendation of at least 7 points to assume. Let's look at only one of the points and what is the procedure for it. That point is the second point we're going to assume, which is 0.02 here. So this is the first step. Assume the 100 P0 to be 2%. We're assuming the 0.02 times 100, it's the 2%, the second column that we need for the curve. Clear so far? Assume this, multiply it by 100 here. This is it for the first 2 columns. Clear?
Yes.
All right.
Yes.
Second step, the P0, the 0.02, we simply multiply by the entire small n that we have, which is 89 from our plan design here, which is 89, and then we would have 1.8, right? We now have 1.8. That 1.8 is a value in a table that we go find 1.8 in addition to what is the C value that we have, and we simply read the probability from the table, and the probability is 0.731. We simply put it here. In our curve, this is the 0.731. This is the point, this one right here. That's for the assumption of 0.02, the second assumption. For the first assumption, it's here, which had a probability of 93.8%, right here. Also, just a value from a table. We're going to look at it next time. We're going to look at the table and see how we can find those values based on the C value that is given, or we assumed in our design, in addition to the effect of the sample size multiplied by the assumption to just create that operating characteristics curve. Then after we do all the points, then we can use this based on, if we take a sample, find its percent defective, from it we can know what is the probability of acceptance of the lot. So we can make our decision based on a probability, not just a specific binary decision and that's it. What is the probability of actually accepting and rejecting the lot? We're going to discuss this further. I'm going to repeat talking about this slide again in the next lecture. But for now, you should know, since our C equals to 2, we will find a percentage. We will find a percentage that is appropriate with accepting. If it's 2, we accept, right? If it's 1, we also accept. If it's 0, we also accept. So our probability here is the probability of 2 and less. So it's 2 and 1 and 0, all three probabilities. From the table, we simply read the cumulative value for P2, which is just written in the table as 0.731, right? There is no work on you. You're simply getting a value from a table, which is the cumulative value. That's it. I'm gonna repeat all of this again next lecture. Okay, we're gonna pick up from here on Sunday. Any questions?
Yes, doctor.
Yes, please.
Regarding the attendance, I joined the class after maybe 5 minutes.
Okay.
About 107.
Other than that, any questions about the content of the lecture? Before that, I'll get to the attendance in a minute.
Okay.
Any other questions?
يعطيك العافية.
That's it? All good? Okay. All right. So I'll see you guys on Sunday. People who still have attendance issues, stay in the meeting. Otherwise, please leave and I'll see you on Sunday.
يعطيك العافية يا دكتور.
Allah يعافيك. توفيق. Okay. Who has an attendance issue?
مين محمد العمود.
Good afternoon, everyone.
The class after.
Repeat one between discuss with non-accepted samples, and the first sequential sampling is bigger sample. You reject a lot, correct? Good. Wasim Abdel Basit.